This video presents the investigation of delayed fracture in metal-stable austenitic steels. Part of this investigation is in cooperation with the Subproject in the frame of SFB 761 steel ab initio. Due to the reduced amount of nickel as alloying element, they are quite cost competitive compared to the conventional stable austenitic steels like 316. They obtain outstanding strength and formability through austenite to martensite transformation during plastic deformation. However, the highly deformed parts are susceptible to delayed fracture. Delayed fracture is a material failure occurring in hours or days after successful forming with no warning in advance. Understanding and preventing this failure process is extraordinarily important for extending the material's application. This research studies three main influencing factors on delayed fracture behavior: the austenite stability, the residual stress, and hydrogen content. Hydrogen content in the specimen can be modified by cathodic hydrogen charging in sulfuric acid for different times before the deep joint test. Deep joint test is performed with Harrison sheet testing machine. The blank circled specimen is drawn through with the cylinder punch under controlled blank hold force, forming temperature, and forming velocity. After drawing, the specimen is cleaned and inspected under microscope to trace the fracture initiation. On another specimen, under exactly the same forming conditions, the transformed martensitic fraction along the specimen is measured with a ferroscope. The residual stress is measured with the sectioning method before any stress relief due to the fracture initiation. The results reveal the metal-stable austenitic steels obtain high martensitic transformation ratio at the specimen flank. This martensitic transformation introduces not only microstructure defects like dislocations, but also quick diffusion paths for hydrogen to the crack tips. Hydrogen is observed to settle down the incubation time to fracture exponentially. The fracture surface changes from ductile to brittle with increasing hydrogen content. Based on this study, the critical hydrogen content for metal-stable austenitic stainless steels at certain deep joint conditions can be determined.